One question we can ask about spectral processing is it possible to go from the time domain to the spectral domain and back to the time domain again without any loss? Can we just do the transforms without distorting our signal? One thing that helps with this is that the fast Fourier transform can be inverted with an inverse fast Fourier transform. And this is a lossless operation in principle. Numerically, there's a little bit of distortion typically, but it's accurate to many decimal places. So for essentially, we consider it to be lossless. That brings us to windowing. So a very simple approach you could take is shown in this diagram here, where suppose we just take non-overlapping windows that are just concatenated with each other. We take each window, we perform a Fourier transform, an inverse Fourier transform, then we get exactly the same window back. And if we do that window by window and splice them together, then yes, of course, we can reconstruct the input signal. However, in practice, if we're going to do any kind of actual processing, we want to multiply these spectral frames by smoothing windows. We saw that when we talked about spectral centroid. The purpose of the smoothing window is to eliminate discontinuities at the edges of these frames. And so windowing is really important, and when we apply windows, we can no longer just splice these frames together and have the result be lossless. So that brings us to overlapping windows. So imagine the first case here where we have triangular windows. So I think it's pretty obvious if we have triangular windows and a 50% overlap that when we sum up these windowed samples, the sum will be 1. So in fact, we could use triangular windows and get perfect reconstruction. More typically, we use a function often called a raised cosine window. And what that is just a cosine function, but it's offset and scaled so that the bottom point here is 0 and the top part is 1. And just one cycle of this cosine from the 0 point up to the peak and back to 0 forms a nice rounded smooth window. And if we overlap those by 50%, you can sort of see in this diagram there's some kind of symmetry going on here, and these actually sum up to 1. So that gives us hope, but here's another problem. We want to apply windows twice. We want to, first of all, in the time domain, apply the window, do an FFT, do some processing on the signal, which is going to change it, do an inverse FFT, and when we come out, because we altered the signal over here, the inverse FFT is not going to give us this smoothly windowed function anymore. The boundaries may no longer go down to 0, and so to avoid discontinuities, we want to multiply by a window again. So we've got 2 window multiplies, or essentially effectively the window function squared. So now the question is, can we do some kind of overlap add with the window function squared? And what would that window look like? Well, it turns out that if we take this raised cosine function, even if we square it, if we use a 25% overlap, or maybe I should have said 25% step size, it's actually technically, I guess that's a 75% overlap. Then when we sum up these raised cosine squared windows, they sum up to 1. It's not entirely intuitive, so a really good exercise is to prove, to actually mathematically prove using trig identities that if you take this raised cosine function and square it and then add it to itself, shifted 4 times in 25% shifts, that the sum is identical to 1.